Good, good. Okay. So, as I said, I'll be introducing what I call software and algorithmic approaches to quantum error mitigation. One of the fundamental feature of today's quantum computer, in my opinion, is its sensitivity to noise, to the disturbance of environment noise, as well as sensitivity to the control discrepancies or imprecisions in the controls. So in this series, I'm going in this first lecture, I'm going to talk about what are these fundamental features and what are these quantum computers like, and how do we really use them? How do we deploy useful applications on them? So topic today is on quantum error mitigation. And a brief outline, I'm going to, since this is the first of the series, I'm going to talk about the state of quantum computation and put the emphasis on describing noisy quantum systems. And then I'm going to introduce a series of software and algorithmic approaches to mitigate those noise, both from beautiful prior work as well as some recent work that collaborators and I have been doing. And I'll wrap up with some discussion on what are some interesting approaches that needs to be done. So that's the outline. Now, let me begin by saying that I think we are in a very exciting time for doing quantum computation research. That's because quantum computers are getting more and more accessible through cloud access, thanks to many of the efforts in the industry, such as IBM, Amazon, Microsoft, etc. They are also getting more and more powerful. In the past few decades, the quantum computer that's been deployed and made publicly available has been powerful enough to do some non-trivial computational tasks that we think classical computer or conventional digital computer might struggle with. There's a notion of quantum advantage that the community thinks as a milestone for quantum computer is when we can perform some computational tasks that are will be infeasible for digital computer to complete. This is an ongoing sort of race between quantum computer, noisy quantum system today, as well as the classical or digital algorithms and supercomputers. And I also want to say that because we can play with these emerging quantum computers, it's very exciting for computer systems researcher like me. I don't personally build these computers, but now we can play with it and study how do we really make these computers better, or how to run existing algorithm on these noisy computers in a more efficient way. In my opinion, there are some, the experimental progress is remarkable. We can see how the system size, which is the horizontal axis, increase over the years, as well as in the vertical axis, the error tolerance. In other words, the error rates are getting smaller and smaller as we go up vertically. So we are passing this boundary where we think a classical simulation of brute force simulation of quantum computation is going to be intractable in modern supercomputers, and that's where I draw these dashed line. And existing algorithms, famous ones like Shor's factoring algorithms or Grover's search algorithm, as well as some recently developed near-term algorithms, they still require more sort of a larger number of qubits than we can provide today in order to really see the advantage of running these algorithms for the problem. And the error rate requirement is still very high because the algorithm needs to run for a certain duration, and our current quantum computer might not have enough of coherence time to complete those tasks, or the number of gates just exceeds the inverse of the rate of error in this machine, and an algorithm might fail at the end of the computation. So that's a problem. Let me summarize what I just described. The technological challenge. One is system size. The algorithm that we know today require thousands of qubits and very deep circuit to complete. For those of you who are not familiar with the quantum circuit diagram, I'm just drawing a schematics here, but the horizontal lines in the diagram is the qubits, and the more qubits, the more not lines you will have. And the boxes here are the quantum gates, and a quantum gate can be act on a single qubit, or they can act on multiple qubits. But as you can see, typically an algorithm will involve many of these quantum gates on the circuit. But the systems that we have today are still relatively small, in the range of 10 to 100 qubits. And I think roughly on the order of 100 qubits machine are being deployed and are accessible through some of the cloud access platforms. But it's really hard to execute these large computation on these small machines. The second technical challenge, as I mentioned, is system sort of fidelity. And when I say fidelity, I really meant two things. First, whenever you perform a quantum gate, there are some chance that this gate can go wrong. And on average, depending on different technology, these gates might go wrong in 1 out of 1,000 operation, or 1 in 10,000, 100,000 operations. This means that if you want a successful computation, you really need to finish all the computation you need within a few thousand gates. To add to the problem, qubit has limited lifetime because it's so sensitive to the interference with the environment. If we are not carefully isolate the qubit with the environment, then it can quickly decohere and lose the information stored in the qubit. And typically these qubits today being built have enough lifetime to be able to execute tens of thousands quantum gates. So with all that, there are so many ways that quantum computation can go wrong. I think just showing this is not very informative. We really need to understand what are the sources of error and how do we avoid them or mitigate them. So for the remaining of the talk, I'm going to dive into how noisy are the quantum computers and what are the sources of error and what are some key ideas for mitigating them. Before I move on, are there any questions? Feel free to interrupt. I think that will make the talk more interactive and fun. Okay, if not, let me keep going. And as I said, whenever you have questions, don't hesitate to interrupt me. So an alternative title for this talk, in my opinion, would be great ideas, great software and algorithmic ideas for noise mitigation. In other words, a quantum engineer survival kit in order to really do well or perform computation on a quantum computers today. Even though my focus today will be on the software side, I want to say that huge amount of effort has been put into the hardware to combat noise, and will not do justice to noise mitigation without mentioning them. But for the interest of time, I'm going to only focus on the software mitigation strategies. But let me first mention some of the basic hardware side on the bottom. In my opinion, these strategies are used for during fabrication time. In other words, it's helping to build a quantum computer better, to fabricate it better. And the common themes of different strategies are first to discover really stable qubit materials, discover new materials using different technologies that can store quantum information coherently in a long time, as well as exposing just enough control over this quantum bit, because storage of quantum information is not enough. We want to process quantum information efficiently as well. Secondly, once you have a defined material for storing quantum information, you want to improve the synthesis or fabrication of this material. When in many of the technologies, such as superconducting technologies, these are sort of man-made atom quantum mechanical objects, and fabrication is crucial because any defect in these qubits will coming later as non-perfect isolation with the environment or residual interaction with the rest of the system, etc. So fabrication is very important. And thirdly, once you have all these fabricated, you have to have a well-defined set of device parameters to optimize for, and also think about what are the efficient computational gates to apply to these qubits in order to accomplish logic gates. So with that, I'm going to switch gear to talk about what can we do after all these have been done and quantum computers have been deployed. As a user or as a systems researcher, how do we mitigate noise? How do we improve performance of a quantum computation after they have been fabricated? So when I say software approach, I really mean compile or runtime approaches to noise mitigation. I'm listing here 5 categories. I'm going to go through them one by one, but my focus today are really on the first 3. I'm going to talk about each of them with 1 or 2 techniques that fall into these categories. And they represent some of the, in my opinion, very effective, sometimes surprising strategies to mitigate certain noises. So let me get to the first one, cancel error coherently. And these are the references that I'm going to talk about, but what are these? Before I talk about cancel noise coherently, I really need to introduce what are some noise models, or what can go wrong in a quantum bit. If you if you write down the ideal quantum state, let's say it's a pure state of a single qubit, then it's really a linear combination of 0 and 1 with complex coefficients alpha and beta, satisfying this normalization constraints, alpha squared plus beta squared equals 1. You can also rewrite these two complex numbers using two other real numbers, theta and phi. And using these sort of polar representation of these coefficients, you can plot a quantum state or visualize a quantum state on a sphere drawn on the right hand side, and a quantum state psi is really a point on the surface of the Bloch sphere with a angle theta against the z-axis, and phi with the projection in the xy plane. These two angles will specify a point on the surface of the Bloch sphere. And any transformations of a qubit is really just moving this point around the surface of the Bloch sphere. And with the principles of quantum computation, these transformations are restricted to unitary transformation. In other words, if you write the quantum state alpha beta as a vector, a transformation of the quantum state is really a linear unitary transformation. In other words, you can multiply a unitary matrix on the left of the vector. And it is also convenient to think about transformations or how you move around the Bloch sphere as rotations of the Bloch sphere. And if we define rotations about a axis by theta angle using this formula, matrix exponential and sigma x, y, z's are really the Pauli matrices, then you can really specify what are the transformation that's being done to a qubit using rotations. And there's a constructive way of decomposing any single qubit unitaries into sequence of rotations. First, you rotate about the x-axis by some angle. Second, you rotate about the z-axis by some angle. Finally, rotate by about the x-axis, and you will get to any point from any point on the Bloch sphere. And the reason that I'm introducing rotations is because I'm going to talk about what can go wrong with rotations. And to simplify this problem, let's assume that the only error that could come in and hurt us is systematic errors in rotations. In other words, if you want to rotate about an axis, the only error that could happen is a slight over or under rotation along the same axis. Okay, so assuming that it doesn't change the axis, but it just over or under rotates by a little bit. And when I say by a little bit, this epsilon can really depends on the theta angle that you want to rotate. Okay, so ideally rotations are perfect, but in practice, because of imprecision in control, these can introduce systematic errors. Now, because it's a coherent error in the sense that if you over rotate, maybe if we can rotate it back, we can correct it, right? These errors are non-destructive. In other words, in some sense reversible. The only problem is that you don't know how much over rotation or under rotation you had. So let's simplify this problem even further and then see if we can really correct this type of coherent error. suppose we have a target rotation about the x-axis by a theta angle, and the actual angle, it turns out, is r prime, is just a rotation, extra rotation by theta epsilon. In other words, the larger the angle you want to rotate, the larger the errors that or over rotation you had. So there's a linear dependence on the error, but you don't know the slope of this linear error, and you want to really cancel that out without even knowing what epsilon is. Is that even possible? Well, a key observation is that if this is the error model, you can imagine I want to rotate by 2 pi, 360 degrees, then the rotations is really 2 pi plus 2 pi epsilon. Because rotating by 2 pi is just trivial and identity, you can rewrite it as just rotating by 2 pi epsilon. In other words, we have really isolated a epsilon rotation with, of course, a 2 pi factor. Maybe we can use this tiny angles of 2 pi epsilon to implement the reverse of theta epsilon. In other words, can we use this to implement Rx of negative theta epsilon? Well, I think, in my opinion, a very well-written work in 2004 called the composite pulse. It says it's possible, and the key here is that you can actually do a bunch of rotations to cancel out this theta epsilon, and the theory behind it is called the Chador-Suzuki formula, and actually just a simple, just a special case of that. If I rewrite the rotation that we want, Rx negative theta epsilon, in the matrix exponential form, I can actually say theta over 2 sigma x, specify that as the target, and then decompose it into the summation of 3 different elements, and then perform this product of 3 rotations separately. And by the because of the commutation properties, you can actually quantify the errors or the difference between this sum of in the exponent versus the product form, and it turns out the error term is only epsilon squared dependence. In other words, if you can find 3 different rotations specified by h1, h2, h3, so that they sum up to theta over 2 sigma x, I can actually implement Rx negative theta epsilon up to epsilon squared precision. Well, it turns out indeed you can do that. The 3 rotations are not exactly along the x-axis, but it's along an axis in the xy plane, specified by this phi angle, which is precisely this angle. It turns out that if you rotate along this angle first by 2 pi, rotate along this axis by 4 pi, and then rotate in the first axis by 2 pi again, the combination of these 3 rotations can actually implement the Rx negative theta epsilon, which cancels out our original error. So in other words, pictorially, if you had this epsilon dependence in the error of the rotation, you can bring it down to epsilon squared asymptotic dependence. And in fact, these this is just a simple strategy example to coherently cancel out errors by rotating it a bunch of times. This strategy have been generalized, and for the interest of time, I didn't. I did not list all the subsequent work that improves upon this. But since then, a huge body of work has been relaxing this noise model in to go beyond just the over rotation by theta epsilon to arbitrary unknown error function, as well as to generalizing that to correcting with exponential error suppressions, to generalize this for exponential error suppression. If you are interested, I'm really happy to discuss offline about this. But as you have noticed, this is just one tiny made-up model with over rotations, coherent errors. And we say, well, some strategies can overcome that, but this is not really a realistic noise model. Something more realistic has to take into account the coherence of a qubit. In other words, it's not really coherent within the system, but it interacts with the environment. In other words, if you have a quantum system built, let's say your quantum system is in a quantum state psi, we can actually model the entire process as interaction between the quantum system with the environment phi through a unitary transformation jointly on the system environment model. Ideally, if we don't do anything, they shouldn't interact. So they should really be in a state of psi tensor phi. However, because we haven't perfectly isolated the system from the environment, there could be unitary transformations acting on the system and the environment jointly. Typically, this interaction is unknown and hard to undo because we really don't have control on the environment like nature does. The only control we have is on our system. As a result, the system will lose its information energy to the environment. And from the perspective of the system, it's really decoherence of quantum information. If you write the initial state as a density matrix of the initial system, psi, the output is another density matrix, which is just a traced out density matrix of the joint state after the interaction. You can think of this as interaction, and then nature decide to measure environment, but we don't get to know the measurement outcome, and your system end up to be a stochastic distribution of some other states. And this,
I think there is a question from audience.
Okay.
Right?
Yeah.
Dikshan, are raising hand?
Hi.
Hello.
Sorry.
Hi, Dikshan.
I had a question. Hi. I was wondering regarding the previous slide.
Yeah.
So if there's no way to sort of know what epsilon is there a way that we can know which direction error occurs? As if we have rotation about some angle theta, then does it occur in like theta plus epsilon direction or theta minus epsilon direction, sort of like which direction the angle is deviating?
So are you asking, can we know that if we are under or over rotation?
Yes.
Is there a detection mechanism for that? Is that your question?
Yes, because there is really no way to know epsilon, right?
Yeah. So the beauty of this work also, let me maybe explain and then see if you want more explanation. there's the beauty of this work is that you don't really need to know epsilon, not even the direction of it, whether it's under or over rotation. And when I at the end mentioned that there are some subsequent work to generalize that to nonlinear error model, to arbitrary error functions, you have to give it some boundary constraints, like it doesn't have an error, it's continuous. So if you plot the error function as a function of the theta angle, hopefully the error function is a smooth function, bounded, not infinite. The error goes to 0 at the boundary of no rotations or pi rotation or 2 pi. So within reasonable assumptions about the epsilon, we can actually correct without knowing the specific value or form of the epsilon.
So we're trying to implement this, assuming that there's some error epsilon, then we're trying to undo it by implementing, in this case, Rx at negative theta epsilon, right? So sort of like without really knowing what was the sort of like no way to quantify the amount of error that occurred, how do you sort of like undo the right quantity and sort of overdo it?
So the intuition is exactly on this slide. You don't know the scale of the error. Epsilon can be large or small, but you have the ability to implement really rotation of 2 pi times epsilon. This is in the same scale as theta times epsilon. In other words, if you come up with a combination of the angles that can implement negative theta epsilon in that scale, you can cancel it out. Maybe the short answer is, without knowing epsilon, but you do know how to rotate roughly in the scale of epsilon by specifying 2 pi epsilon or 2 pi. But yeah.
I see. Oh, it is sort of like, the question is, assuming that we know epsilon, how do we undo it? Is that, or I like misunderstand it? This slide?
No, this we don't know epsilon. We just apply 2 pi and it automatically gives us epsilon scale rotation.
I see. So we do know like order of the epsilon, as you said.
We can apply order epsilon rotations without knowing epsilon, the value, right? Anyway, so
I see.
I hope that clarifies a little bit. But if anything's unclear, I can definitely feel free to reach out to me after the talk. Since we have a bunch of techniques to cover, I have to rush through some of them. Yeah, so when the errors are not so appearingly coherent, how do we cancel those errors out? Well, remarkably, there's a well-known technique called dynamical decoupling that really can reverse this type of interaction between systems and environment. For example, if you again model the system as a quantum state psi, the environment as a quantum state phi, if you keep the system idle, the interaction will happen with psi and phi. It turns out that we can invent a sequence of gates that in the ideal case acts trivially on psi. In other words, they combine as an identity. But because we have really transformed the quantum state or jumping around, since the interaction with the environment depends on the quantum state, the coupling between the system and environment, in other words, a U1 interaction at this time step, U2 interaction at this time step, etc., they are going to cancel out. Now, this is only an intuition, but in my opinion, this is really remarkable in the sense that we can mitigate decoherence using this idea of coherent error cancellation. And by doing so, we keep the system in a coherent state for longer. But of course, we said every gate you introduce to the system might introduce errors as well. So follow-up work that I like a lot by Das and others, we're talking about adaptive dynamical decoupling, because every gate, like X, Y gate here that dynamical decoupling requires, they introduce errors to the system. So the more gates you perform, the more errors that you introduce to the system, even though you have decoupled from the environment. So there is a trade-off between how often you do these decoupling strategy. If you do that too often, you are introducing too much error. If you do it too rarely, the system can interact with the environment.
Okay. I have a question. Can I please ask a question?
Yep. Yeah, go ahead.
Yes. My name is Kai Tao. Can you please, from Stony Brook University, could you please go to the previous slide?
Okay. Yeah.
So I am interested. So my current research is in quantum sensing. So I am interested in the unknown U.
Mm-hmm.
So is there a way to model the unknown U, or how do you, maybe is there a mathematical way to model the U, or is it really truly some random stuffs?
Well, it depends on the, in other words, the setup in your system. If you have the Hamiltonian that describes your system, as well as the external controls and a good model for your system, then typically we have some knowledge of what are some dominant U that could happen. For example, I'm going to talk about in this talk crosstalk error. This is sort of a environment system interaction, in the sense that if you know how two qubits interact, namely how you couple two qubits in hardware, this will allow certain energy exchange between qubits. Then this open up a channel for potential unwanted interaction with your neighboring qubits. And if you have that model, then of course we can have a mathematical model, or at least to first order what is the unitary U. In quantum sensing, I'm afraid typically this is I'm afraid I'm not the expert to answer in the context of quantum sensing, but I would imagine if you have some knowledge about your detection system, in our context is the computational system, then you could have a model for what are the first order interaction that could happen between the detection system to the environment or system that you want to perform sensing on.
Okay, I see. Thank you.
Yeah. Okay. So this is still a so far we have discussed how to cancel out errors coherently, right? In some sense, the setup of the problem naturally allows errors to cancel out or be reversed, even though you might not know exactly how much error happened. But other times, this is not possible. And the best you can do is to avoid noisy operations. And there are some strategies in that category as well. If you look at the system level architecture, the performance is not as ideal as we like. For example, some notable features is that current quantum systems have limited qubit connectivity. For example, not all qubits are connected. Only sparsely connected graph are provided. And then secondly, not all qubits are identical. When we design algorithm, we typically assume that we have a bunch of qubits to work with and they are equivalent. But in practice, each qubit is different. For example, on the right-hand side, I pulled the data from IBM quantum systems. And you can see that in the superconducting transmon architecture that they used, each qubit has their own frequencies. They all have different sort of coherence time. And as we mentioned earlier, qubit has limited lifetime, and you can see there's a variation in how long each qubit can stay coherent. And using this observation, when we have a quantum algorithm and want to map it, run it on the given quantum computer, we really need to be aware of the noise. On the left-hand side, I'm just showing a schematic of the amount of interaction required by application. The application is not important here. It is the metastate distillation protocols. It uses a bunch of qubits, which is represented as nodes here. And every edge here is a 2-qubit gate between the incident nodes or incident qubits. As you can see, they are not uniform either. Given an application, some qubits need to interact strongly. Others, you can keep them non-interacting. And the problem of mapping a application interaction onto the given device or connectivity of qubits is a well-known qubit mapping problem. And in the context of noise and noise-aware qubit mapping, since some qubits are more erroneous or have have less coherence time, you want to be strategic about where do you assign your computation to, right? If you have a high error qubit over here, maybe you want to avoid it. And there's a line of work that uses strategies, heuristics, or different methods to figure out what kind of mapping will give you overall success rate a boost. So this is a class of strategies. Just to follow up with that, in a similar vein, each gates is different. When we design algorithm, again, we would assume that when we want a CNOT gate, it really accomplished a CNOT gate. But in practice, it's hard to individually address gates. And when I say individually address, I mean, if you want to perform 2 gates, this is just an example of parallel unitary gates on different qubits. Ideally, you would assume that they accomplish U1 on 2 qubits, U2 on the other 2 qubits. However, in practice, because they are right next to each other and there are channels for the 2 adjacent qubits to interact, even though we try our best to disable this interaction, there might be some residual unwanted interaction going on between the 2 gates. And then the computation you accomplish is not just U1 tensor U2, it's something else. So I'm going to go through how one might approach mitigating this type of crosstalk error, but in a really fast way, since we are short on time. So in order to understand this crosstalk error, we can and the approach that I'm going to introduce, I'm going to very briefly talk about what is the superconducting qubit that we are given, the system that we operate on. So a qubit state is used, we use transpond energy levels to store the state of a qubit. For example, if you wanted alpha 0 plus beta 1, then we really want population alpha on the ground state E0 and then beta on the excited state E1. Typically, when we build these quantum mechanical systems, it's not just two levels, and there could be high energy levels. And if you have populations going up to the high level, that's going out of your computational subspace because you only wanted everything to stay within the first two levels. Going to the higher levels is called leakage of information. The actual implementation of the qubit in tunable's transmon setting is really this circuit consisting of capacitors and Josephson junctions and some drive signals. For example, the flux drive, if you have flux drive through this loop of Josephson junction, then you can tune the frequency of the qubit. And if you send in DC microwave drive through this line, then you are going to perform rotations of the qubit, as we discussed earlier. Something that's not maybe not familiar to all of you is the tuning of the frequency of the qubit. You can do that by adding external magnetic flux to through this loop, and it will change the frequency of the qubits accordingly. And the reason I'm introducing these is because even though this all look very hardware design layer, we can actually expose lots of parameters to the software. And then I'm going to introduce how do you use a really software approach to control these parameters to improve the noise resilience of the device. And this is a slide showing how two qubits are put together and to interact. They interact through resonance. You couple them with a capacitor in the middle, and they can exchange energy through this capacitor. The way that you do that is by changing the frequency of the two qubits. If they have the same frequency, they can interact through this so-called I-swap interaction. And if you make the high level parameter of the two qubits match, then you accomplish a CZ interaction. The particular gate or interaction is not important here, but it's saying that changing the frequency will make your two qubits interact or not. And if you interact in the wrong time step, it's called crosstalk. So as I said, each qubit has a frequency predetermined. I'm plotting that here. But notice that these two qubits have really close frequency and they have a connection between the two. So they can interact. That's not very good. This is called frequency crowding. Accidental qubit interaction due to how close the frequencies are. They can also, they become very prominent when you do quantum gates in parallel. As I mentioned that because you want to interact Q1, Q2 by tuning the frequency of these two qubits, and then interact Q3, Q4 with the frequency tuning, If it happens that they are all tuned to some frequency that's close to each other, then these two qubits will also talk to each other, causing unwanted crosstalk. So it's all about changing the frequencies of qubits, it appears. Then the natural approach is to avoid assigning same frequency to neighboring gates. Well, a software can do that, right? Indeed, if we just take an application, say I wanted all these qubits to interact, qubits boxed in a red box, then let's try to assign different frequencies for each of the box so that they don't interfere with each other. If we map this to the graph, where each of the dot here is a possible two qubit interaction, then we have highlighted the ones that we want interaction to happen, and all the gray ones are the ones that we don't want any interactions. It's really about a coloring of the subgraph for the interaction graph, because you don't want these two boxes to have the same frequency. We want to assign two different colors to them. In other words, you can visualize the frequency chosen for each of the two qubit gates like this. A graph coloring algorithm in software can do this. And indeed, if we measure, this is what we did in our work 2 years ago. You measure the average crosstalk strength before assigning really using graph coloring, and after graph coloring, you can lower the average crosstalk strength by a huge amount. And I'm going to skip this part, which is mitigating leakage, also by introducing extra constraints in graph coloring algorithm, and you can reduce crosstalk further. So the message I want to convey here is that a lot of the hardware parameters are really difficult to tune by hand, and a software can actually easily do this automatically, and that gives us opportunity for software approach to mitigating crosstalk error. And it's against, as you can see, this is the full framework that I'm not going to go into the details, but if you have a full computation, the algorithm can decide what frequency to assign to each gates, to each qubit, so that the whole process will create low crosstalk overall. So this is some data showing that the really the red bars, which is after coloring, can accomplish high success rate, so higher is better in this bar chart, for a wide range of benchmarks in the x-axis, compared to the baseline where you don't have the ability to tune the qubits for different frequencies. Okay, so I think I need to wrap up soon, but let me quickly go through the strategy that I didn't get the chance to mention in this talk. First one is synthesizing robust operation directly. Like how do you design an operation from scratch that is very robust? When I say operations, this can be done in multiple levels. When we are dealing with the pulse level, this is a great framework called quantum optimal control. And if we are doing this in the gate level or circuit level, then this method of variational ansat for really noise aware variational ansat is the way to mitigate noise in the circuit level. So I'm not going to go into the details of the strategies here, but the idea is that you have a bunch of control parameters, theta, and you know how this system will evolve. You have an objective function for where the quantum state that you want to get to, then it's an optimization problem, right? The standard approach in quantum optimal control is to make it numerically feasible. You discretize the time for the control because the control could be time dependent. You discretize it to different time steps, and you have a bunch of control parameters at each time step, and compute the derivative of the objective function with respect to the control parameters. And you want to use gradient descent search to find a good set of parameters to accomplish this minimization problem. And one example is that you want to reach a target state psi ideal, and you want to minimize errors that of the output state. This is done at the pulse level, and you can also do that at the gate level. And similarly, you have a bunch of parameters for the gates. In other words, a parameterized quantum circuit, and you can look at how you want the output state psi of theta to be, and if you have an objective function for with respect to the output state that you prepare, then you can perform a optimization loop following strategies similar to what I just described earlier in the optimal control framework. And I'm going to skip this, showing that we can do that efficiently at the gate level to really design a variational onside for particular Hamiltonian simulation or variational quantum eigensolver problem. And in the context of noise, our strategy can perform really well. Let me just use one sentence for each of the remaining strategies, classes of strategies, just to encourage sort of discussion on what kind of new strategies that we can develop. One idea that I like really very much is engineering errors. Because these quantum devices are so noisy, sometimes you can actually drive the errors to one way or another that you desire. For example, if you can form you can build a device that has high Z error, but very, very low, let's say low Z error, but very high X and Y error, then you can design algorithms to take advantage of that bias noise. And maybe that because of the bias noise, they are easier to correct. And also randomized compiling is a strategy for converting coherent errors to incoherent errors or stochastic errors, or even with the Pauli twirling argument, you can you can convert errors into depolarizing channel that potentially are easier to correct or detect. There are also strategies that deals with the output even when errors happen. After error happens, you can use classical post-processing to carefully remove some of the noise in your data that you get from performing the computation. So these are some different angles to mitigating noise in this context. And let me just wrap up there because we have gone through a bunch of strategies. So I list the summary slide here, and I'm happy to take more questions. Thank you.
Hi. Can you hear me?
Yeah,
Hi, Professor.
I can
So
hear you.
I do have a small question. So
Yeah.
so so in the tunable superconducting qubits,
Okay.
that's for the avoid that's a technique for avoiding the noise, right?
Mm-hmm. Avoiding
And
crosstalk. Yeah.
yeah. I just have a thought that is there any like is there any arrow that no matter how you tune it, um the crosstalk will always exist, and maybe we can like use the use a reverse gate to reverse operation to undo it. Like, is
Mm.
there a situation like that? I'm just really curious about that.
It sounds to me that you are trying to combine the ideas
Yeah.
of canceling coherent errors and avoiding crosstalk. Is that fair?
Yes.
And
Because
you're
I suppose
asking,
crosstalk and
yeah,
decoherence are kind of like the same thing. Like from the like kind of they're kind of like the environment arrows.
yeah. I know that in the adaptive dynamical decoupling work, they found that dynamical decoupling indeed can reduce some level of crosstalk. Um, uh, I would say that because here we know what gates that we are performing. For example, the parallel CNOT gate. Let's use the right-hand side here. We're
Okay.
performing two CNOT gates here. And it's not immediately clear to me how you would decouple this interaction during the execution of the two gates. I can imagine that one way you can do that is to first serialize these two gates, assuming that they are not parallel anymore. But because the qubits might still have crosstalk with the gates, you can try to apply dynamical decoupling on the idle qubits to decouple the potential crosstalk to the CNOT gate on the other qubits. I would be interested in to see how effective that can be. I can imagine there's a trade-off of how often you add dynamical decoupling versus how much tuning that you can do to the system.
Yeah, I do suppose that. All right. Yeah, got it. Thank you.
Mm-hmm. Let me pull up the summary slide so I can remind you what was discussed. Great. Yeah.
I have a small question actually. So, for the first technique, how can we assume that the over rotation is like linear to the theta? So why is it just a linear relation? Yeah.
Right. So that's a great question. This is not a realistic model. That's the short answer. This is just a simplified model so that I can introduce this technique conveniently. Indeed, in this composite pulse work, this is assumed. And okay, so let me back up. This linear relation does happen in many cases. I think in NMR, you have amplitudes damping type of errors that might have similar characteristic as this linear dependence. But I also want to say that since the invention of these composite pulses, people have been relaxing these constraints to go beyond linear dependence. And in fact, I didn't get the chance to introduce, there's a way to mitigate arbitrary error function. Suppose this is a polynomial of degree d, not a linear function, but high degree polynomial error function. Then you can actually use roughly 2d number of pulses to exponentially suppress this this error. In other words, you can suppress these errors to epsilon to the d, where d is the degree. The strategy there is polynomial interpolation. Very beautiful results. Yeah.
Okay, got it. Thank you.